building photoreal worlds in Unreal Engine 5.2. So, oops, sorry, double click. Let's start with PCG framework, because that's the thing I work on. So what is PCG framework? It's a fast and iterative procedural content generation framework in Unreal for world creators. So basically, we're trying to provide you tools so you can build your own solution for whatever procedural thing you want to do in your game, your movie, or any kind of project. So why are we here? Well, as you might know, in UE5, we released world partition, and that allows you to build bigger worlds. And with bigger worlds, you need more content. And procedural is a pretty good way to approach that problem. So that's exactly what we've done in the Matrix Awakens demo. We've built this incredible city, all procedurally done, and it was awesome, right? But we kind of noticed there were some production challenges, workflow issues that we wanted to try to address. And as you might have heard just a couple of minutes ago, with UEFN, more and more people are going to have their hands on UE, and we wanted to make procedural content generation a lot more accessible. So all of this drives the vision of what we're trying to accomplish here. We want procedural content generation in Unreal Engine, so no reliance on external processes, even though, you can add them if you want to. Runtime and live editing focus, so you can use procedural content in your games at runtime, or at least have a very good iteration speed in the editor. Because it's procedural and deterministic, you're going to have non-destructive workflows, and you're going to be able to do manual interactions, as you've seen in the demo. And finally, it's a framework, right? So it needs to be easy to extend. And we'll dive a bit more into that later. So the overall concept is nothing very new. Looks a bit like materials. Like materials, you have materials, material instances, and material graphs. So we're starting from the bottom here. We're introducing a new thing called the PCG graph, which I'm going to talk to you about in a second. At the instance level, we have the PCG component, well, it's basically the graph you want to run, and at some point in the future, some parameters so you can tweak. And somewhere in the future, we're expecting to have, what you see is what you get assets that you drag and drop. You have a couple of sliders, and it just behaves the way you would expect it to. So let's talk about the node graph. It's an editor like, maybe something standard like the material editor. You're able to drag new nodes, drag pins, or in your right-click, add something. There's a node palette on the left side, which will actually show the nodes you've created yourself if you want to. You have the settings on the right-hand side in this case, where you can tweak whatever you want. And because it's procedural, you want to be able to see the results. So any node you can inspect, see the results, the properties, the points, the metadata. You can also turn on visual debugging, so you can show cubes or whatever mesh you want. But as you might have seen already, everything is interactive. You change the parameter, it shows up live. You add a new node, it shows up live. You remove something, it shows up live. You can also change the landscape, and it'll update. So it makes for a very interactive experience, and it's very useful, and hopefully you guys will like it. So let's dive in a bit more on the data side of things. So conceptually, in PCG, data is a probability density function. So that means that you're going to expect density values from between 0 and 1. So let's take one example, the landscape here, right? If you're on the landscape, density is 1. If you're outside of the landscape, density is 0. To take another surface example, well, if it's a texture, well, density can be driven by the pixel color, for example. So you can have values in between 0 and 1. That mathematical approach enables you to do intersections, unions, differences, interpolation, and be able to be very precise on exactly what you want to do. Concretely, we've already mapped a couple of engine types to be able to use in PCG. So landscape, you can raycast against the physics or overlaps. You can use splines, landscape splines, any kind of volume, primitives, collision shapes. But most of these you'll end up sampling from, and then you end up with points. And points are the core data type in PCG. So basically, points are very simple things: transform, bounds, density, and then some metadata. And metadata is what you're going to use, well, attributes, to build logic in your graph and come up with something cool. On the node side of things, the nodes basically, they do one of either two things. They do transform data, or they spawn or create artifacts, so spawning meshes, spawning actors, or any kind of resource you want to track. And PCG is going to help you to track those and manage those like transparently. Of course, on the nodes, you can set up whatever value you want. Like this is a transform node, so you can say, okay, I'm going to change the rotation from minus 45 degrees to plus 45 degrees or something. But maybe more importantly, in native nodes, if you tag your properties as overridable, you can easily have the pins. Well, it's automatic, actually. You're going to have the pins so you can dynamically drive those values in the graph. If you're using a node created from a blueprint, any instance editable variable also will create those pins. And those pins will allow you to create logic and, in between the different data types or data in your graph. So let's say you build some trees. Maybe you want to put roots around them, right? So you want to keep them in a logic way in your graph. Right. We're already providing you a small library of a bit more than 40 native nodes. But maybe more importantly, we're still providing you with blueprints. And that kind of ties in the next slide, which is extensibility. At the moment, it's very easy for a technical artist, or even less technical artists, to build a blueprint node for PCG. You derive from the PCG blueprint element class. You implement the execute with context method, and then you could use one of the loops we provide you if you need to loop on some points. And this loop is going to be multi-threaded by default. You just need to implement the body. And that allows you also to not only be quite faster, but sidestep some of the blueprint limitations, like the number of iterations. But you're still in blueprint, so you have access to everything in the engine. All right. On the execution side of things, I've already told you the nodes can be multi-threaded, and that's true. The graph itself can run multi-threaded as well. If multiple nodes, their inputs are previously computed, well, we can run them in parallel. But maybe a bit more importantly, for runtime purposes and live editing, everything can be time sliced as well. It's pretty simple to do, and it's something we can expand on in the future as well. And that's very useful for games that want to do runtime generation. Finally, we have a cache to allow iterations very quickly in the editor. So if you change just a part of the graph, well, we don't need to recompute the rest. It's already computed once. We've cached those values before. All right, so all of this is exciting. Hopefully, you guys are excited as well. But this is experimental 5.2, right? So don't get too attached to the UI or the API. We're still working on these. But we want to try to make these as simple as possible. So we'll streamline the APIs, we'll extend more stuff. And there's a couple of big topics that we're going to work on in the next couple of months and the next couple of releases. The first being graph LEDs. And JS will give you a good example and a good justification of that a bit later. We'll look into GPU microscattering soon enough, and we need to address a couple of production things, like per platform settings or different workflows. Sometimes you want to bake everything to the final game or something. But that's it for me. Hopefully you're still excited, and I'm going to leave you in the hands of the very capable JS to talk to you a bit more about the path we've taken to get to the electric Dreams demo. Thanks a lot, guys.
Thank you, Julien. My name is Jean-Sébastien Gay, and I'm a technical art director working with the Unreal Engine development team on procedural and world building. We started working on the PCG framework just about over a year ago, and we were able to build the Electric Dreams demo that was presented earlier in the keynote by leveraging all of the groundwork and internal prototypes that we did throughout that development year. So let me start by showing you some of the most important ones. It was clear for us that the framework had to support runtime and live editing. We started by doing gameplay prototypes in the Lyra Simple project, as we think that there's nothing else quite like games to prove the point. As you know, in-game means unpredictable pair input. And that's cool. That's what we want. That's what we love about games. But our procedural framework needs to answer to that with predictable, deterministic procedural outputs. And that's extremely important. To test that, we built 2 simple prototypes with different variants for each. The first one combined control point mechanic and PCG. When a team captures a point, we spawn visuals around it, as well as new extra control points, expanding the gameplay area up to a defined grid size. The team controlling more than 50% of the area wins. The second prototype is an infinite runner, where a single difficulty variable is incremented every time a player crosses a tile. This variable is then impacting the results of the upcoming tile, by increasing the density of what's coming up. And we made also a quick alternate version by adding a random rotation to those tiles, and then we updated the PCG graph to have arrows indicating where the player should go, and that was done fairly quickly. Actually, these multiple prototypes were built under 2 weeks by only 2 technical artists. And it allowed us to confirm that having that framework working at runtime within Unreal Engine for in-game and multiplayer content is an idea totally worth pursuing. Ultimately, we think that this framework can bring new gameplay opportunities for game devs. Next, we wanted to attack scale and speed in a much higher density in a large world. The demo was about switching realities using Fortnite, City Sample, and Quixel content. Here in the video, you can see the Fortnite variants being generated live during gameplay. It is made of 4 different PCG rules. It is made of a single PCG rule with 4 different presets. And they're applied when the player goes through those portals. To achieve this, we had to build a custom hierarchical generation logic in Blueprint as a way to support level of detail based on distance and orientation from the player. This hierarchical generation concept is to be implemented natively in the framework in the very near future. As with the gameplay prototype, this was all running at game time in a quick build, without any pre-generation during the quick time. Working on these really helped us on improving performance, multi-threading, scale, and parameterization. But, well, that's not all. We had to build well-building tools prototypes. We want this framework to be used by artists and designers to create their own tools for their own project needs. It's an open framework. It is not limited to a single task or domain. In this video, you can see the interrupt with the geometry tools to separate biomes using volumes, which are then processed within the PCG graph. But we obviously had to try some building generators, what would not have been called PCG, right? So the first one here shows handles to define the footprint of the building, and then construct it using City Sample City Sample nanite modules. The second prototype here is a little bit more involved, as it's reproducing the concept of a defined grammar as used in the Matrix Awakens buildings. For each floor, the grammar is set within the node graph in this case, and adapts to the spline driving the footprint. So after seeing the great assemblies that the Quixel team was producing for this demo, we thought that it was a good opportunity to start looking about how we could be leveraging and crafting and procedural all together. We started working on what we call the PCG assets that can be used inside as instance nodes within the node graph. These assets basically stores a point cloud of all visuals contained within a level, with a full set of attributes, such as the mesh and material references, the scene hierarchy, and actor tags. With all that information accessible, it is then possible to augment these assemblies through procedural logic and increase iteration speed and quality overall. The lower half of the video here shows you how simple the rule actually is given the results above. You can also see the attribute list view being updated live as I'm extending the spline and enabling disabling nodes. The asset utility is distributed with the PCG plugin, so you can use it, just improve it, or use it as an example to create your own PCG assets type if you want. All of what I've shown here so far proves that we need to build for extensibility and interactivity. Effectively, what we want to do here is to blur the lines between procedural and traditional workflows. We believe that procedural tools should always help artists and designers to reach the best quality possible in the project's given time. Okay, enough of the prototype work, and let's jump into Electric Dreams. That was a nice music. Okay, so our objective with this demo was to show how scalable the solution already is using everything that we've learned and developed so far. We are literally generating pebbles up to the large Vista mountains in the background. We have 8 unique PCG graph total in this world, supporting complex multi-graph interactions and full parameterization. And we're also leveraging the concept of the augmented PCG assemblies that I've just talked about. Now, what we call the close-range PCG area is made of 4 of the 8 PCG graphs. There's the small and large assemblies, the ground, and the embankment sides surrounding the area. Within the PCG graph, you can get data from actors, and you can get even outputs from other graphs. The ground rule is a perfect example of multi-graph interactions because it's using all of its neighbors to construct itself. It starts by getting the embankment spline to create its surface. And then when adding the assembly to the world, the graph gets updated. And during that update, we compute a distance field to rotate points around the assembly to better conform them around its shape. Using our debug visuals that can be customized and applied to any node or to multiple nodes at the same time, we can see here the ground surface following the embankment spline and what's actually happening underneath the assembly when it's present in the scene. By moving that assembly left and right, we get callbacks triggering the graph update, and we respawn everything that has been changed by that manual interaction. The ground rule is not the only example with complex interactions. The large assembly itself is also aware of the embankment and the small assembly next to it. A good example is the fall-in tree logic within that rule. The surrounding spline is used to find potential fall-in tree target position, which are represented by the blue wireframe box in the image that are quite hard to see, I'm sorry. By testing for overlap between the potential fall-in tree bounding volumes and these targets, we can define if the tree should be spawned horizontally, pointing down toward the ground, or just discarded completely. We can control the probability by adjusting the number of potential targets in trees, but we could also use helpers to precisely place one specific fall-in tree if we want. Speaking of helpers, in the large assembly, we added lens slice manipulators. And these can be used to customize the assembly interactively with full manual control. And then it was super easy to integrate the same logic when we are approaching the small assembly next to the large one. And this is the kind of interaction that we expect you to build and expand on when creating your tools with this framework. Now, the PCG asset prototype shown a few minutes ago has proven to be extremely useful. And that's quite a blinding image. In the upper right corner of the image, you can see the procedural assembly with all of its modules. And the same applies to the embankment rule, where we have specific modules with specific functions, such as the 360 lens slide on the left that can be virtually placed anywhere because, well, it can be rotated, right? And everything in there is scattered along the spline using the segment length, the curvature, and even overrides to address specific art direction calls. But we can also use world raycast on a surface as a surface to sample on. In the case of the clover patches here, we're actually raycasting on the output of the graph itself. Placing such assets using raycasts can return invalid position and causing orientation and floating issues. So we fix that by creating what we call the flat area detector, using the subgraph feature, just like a material function that can be reused. Within that function, we reproject at the corners of all of these patches and define if the object can be safely placed or not based on overlap and orientation of these extra points. So notice the red debug points on the left, and where it's a little bit more flat on the right, we get a lot of green, and that's where you'll see clover being spawned. And this is shown at a very, very small scale, but you can imagine that we're using exactly the same subgraph and the same logic within the forest to spawn rocks at much larger scale. In most cases, we use a static mesh spawner node that outputs optimized instance static meshes component on the actor holding the PCG component. It's not only the most optimal output for the engine, but it's also fully customizable as we've exposed ISM descriptors that can be edited per entry. And these descriptors, you can also create material overrides. And you can even use material overrides by going through per point attributes. And that's what we did a lot in the demo. But we're not limited to ISMs. We can spawn actors, and we have to, obviously. In the case of in this case, we're spawning dynamic rocks and plants all over the area, and we're even excluding the car bonding volume. And excluding the car bonding volume is not a new idea. Remember, in the gameplay prototypes, what we had to do is remove the player from the spawning of the assets, because we don't want any assets being spawned on top of them during gameplay. Okay, let's jump onto the long range. The remaining 4 rules are the vistas, the mountain and base forest rules, and the fog cards. And pictured to the right, which is there, we have the forest graph, which supports the most interaction and customization within the demo. As you can see in this video, we've exposed a set of parameters to quickly exit the forest life. Those parameters come from variables on the blueprint with the PCG component, and then are read back within the graph. While this will always be supported, as Julien said earlier, we're currently actively developing our graph instance system, where you'll be able to expose the parameters directly from within the graph. So you don't have to go through blueprints and variables to do so. A little bit like material parameters, where you want to edit them into the material instances. The forest rule is following what you would expect from a procedural forest, where primary assets such as rocks and trees are surrounded by their own secondary and tertiary assets. And the rocks and the cliff are also removing all of the trees that are overlapping, so we don't have bad overlaps in the forest. And in the same way, we exclude the entire and crafted area, as well as the PCG closed range area that I was talking about earlier. And we are even mixing both the mountains and the base forest rules together to blend them using, again, a subgraph with logic based on height and normals. You can see in the video that's live with the debug display applied on multiple nodes. Using the same parameterization approach, we built different presets for each layer of the Vista rule. The idea here is that we can have different configurations, store them, and apply them when needed, such as an in-game event, or a cinematic, or just multiple shots of a movie you're making. But you could also use those graphs into multiple worlds and across production and project. And within all of the rule of the demo, we heavily rely on attribute operations. And through those operations, we scale things based on distance. We create stacks of mountains and call trees behind those mountains. We reorient the fog cards toward the center of the world. And we even apply different vegetation